Good afternoon, everybody. Welcome back from the weekend. Hope you're having a good Monday so far. I'm going to start us off with a molecule of the day. So we have 5 of these for the upcoming exam, which is going to be on Monday, a week from today. And I'll put that on the board over here in a minute when we start talking about that. But first, this molecule of the day. This is naproxen. So naproxen is a over-the-counter pain reliever that you can buy. It is in the same class as aspirin and ibuprofen. It is a non-steroidal anti-inflammatory drug, or NSAID for short. So it doesn't have a steroidal unit in it. It doesn't have that ring system that we've learned to identify, but it's an anti-inflammatory in the way that steroids they are, and it just doesn't have that structure. So it's also a pain reliever and a fever reducer. And this is its structure right here. So this is naproxen. It has this naphthalene ring, an OCH3, and it's got a carbon with a CH3 and a carboxylic acid functional group. And one of the reasons I thought it was interesting is that industrially it's made using a Grignard reagent. So what you start with if you want to make naproxen is this molecule, and this can be accessed from naphthalene, which is a really readily available hydrocarbon starting material. It's present in gasoline to a pretty large percentage. So it's not easy, not difficult to get a hold of the hydrocarbon ring here, and then you have to get it elaborated and functionalized in these positions. But once you get this Grignard reagent, what happens is that the carbon that the magnesium is attached to is partially negative, and we talked about that. And then if you give it this alkyl halide has a partial positive charge there. This does an SN2 substitution reaction. So we've seen Grignard reagents acting as nucleophiles attacking carbonyls, and that's all the stuff that's in this most recent chapter that we finished. But it can function as a nucleophile and attack in other ways carbons that are electron poor like this and do an SN2 reaction. So that's just another application of Grignard reagents, is using them as nucleophiles in other ways. So it doesn't immediately give you this because you'll notice there's a stereogenic center here, and you get a mixture of both. So once you do that Grignard reaction, you have to do something called a resolution step, because this naproxen is one that is not safe to take as a mixture of enantiomers. Only the S stereoisomer is safe to use and effective. The R enantiomer is, I think, a liver toxin. So it's definitely, you can't just take both. You have to have just the S stereoisomer. And the strategy is you make them both and then you separate them, and you only use the good one. So that's our molecule of the day. We'll have one more that I'll break out either on Wednesday or on Friday. Okay, let's talk about some other stuff. So we've got an exam coming up. Exam 3 is going to be next Monday. It'll be here, unless you've got accommodations to take it elsewhere. It's going to cover all the material that we covered since the last exam. So that'll be what's in the syllabus and the things we've discussed in lecture and the homeworks you've been working through and practicing with. So that's what's coming up. And then after that, it'll be Thanksgiving break. So that'll be a lot of fun. We'll get the exam done, and then we'll go off and have a nice break. Couple of survey questions that were up for today. So I'm going to talk about this first one first, and then we'll talk about the second one. So one of the survey questions, there were 2 content type survey questions. One of them showed you this ester, and then it said, what would happen if you put in the first step this Grignard reagent? Cyclopentyl magnesium bromide, and it says excess, which is just telling you there's more than enough to react as many times as it prefers to. And there were a bunch of options to pick from. It was a multiple choice type question. Well, what happens is Grignard reagents add twice to esters. So without going through the big long mechanism, what I'm going to tell you is that this group functions as a leaving group. So one of the Grignard equivalents comes in and attacks, and the leaving group leaves. technically the electrons go up onto the carbonyl oxygen, they come down, and then they bump out the OCH3. That gives a ketone, and then another one of those equivalents of this Grignard reagent comes and attacks there, and what you end up getting is two of these R groups attached to where the carbonyl was. So the product here is going to be, we get an OH group, and then two of these cyclopentals. So that's the key with esters and acid chlorides, is that you add two equivalents of the organometallic reagent, be it Grignard reagent or organolithium. So that's the product. People did pretty well with this. I looked at the statistics, and it was the majority of people got it, and that was good to see. So excellent. The other one was a question that had to do with, well, it was a predict the reagents type question. So it was one where you got a structure, and you were asked to figure out what would you need to put in to make this reaction happen. So let's take a look at this one. So here it was, you start with an ester, and what would you need for reagents to get it to do this? Form this species, and then you're also told there's a equivalent of ethanol, which is produced in the reaction, and you had to pick from several options of reagents from a list. So what I like to do with these things, if I'm trying to figure out what's going on in a reaction, is see what is different and see what is the same. So if you can find parts of the starting material in the product, that's helpful, because then you know what you need to bring in that's not there to start with. So I'm going to highlight a portion of the molecule that has like some atoms that, if you map these onto the starting material, basically all these atoms that I'm circling are present in the starting material. And then this bit right here, that ends up being this part right here. So what's happening is we're losing the ethyl, the OCH2CH3 group, and we're gaining a couple of pieces. So these are new. These have to come in from some reagent that you add, two methyl groups. And so that looks like addition of either methyl Grignard or methyl lithium reagent to an ester, because they add twice to esters. And in this example, the option that you were given was a Grignard reagent. So there was CH3, Mg, and it could either be a chloride, a bromide, or an iodide. In this particular example, it was a bromide. That would be reagent number 1, and then reagent number 2 would be treat with water. And that would do it. Two equivalents of the methyl magnesium bromide would add to the carbonyl. The first one bumps out the leaving group, making a ketone. Then the second one comes in and attacks the ketone, and you end up getting this tertiary alcohol. So people did well on this one too, so I was happy to see that. So, so looking good. Any questions about the survey? Either of the survey questions? All right, then we're going to shift gears and we're going to talk about aldehydes and ketones some more. We had a pretty healthy dose of aldehyde and ketone in the previous chapter, but there's more to say about them. And that's what's covered in the next chapter, is some additional reactions of aldehydes and ketones, as well as some discussion of how to name them. And that's where this chapter starts out. So this is chapter 18, and it's about aldehydes and ketones. So I'm going to say aldehydes and ketones continued. The book doesn't say continued, but I'm putting it in there as a transition because it's not like the first time we've seen them. It's not our first look at aldehydes and ketones. Just as a quick reminder, though, about what they are and how they differ. They're very closely related, aldehydes and ketones. They both have a carbonyl with an R group. Just aldehydes have an H. Ketones have two R groups, and the two R groups could either be different or they could be the same. Aldehydes tend to be a bit more reactive because they have this smaller H, so sterically it's easier for a nucleophile to attack that carbon. It's also a little bit more electron poor carbon because each one of these R groups gives a little bit of electron density to the carbonyl. So the carbonyl is partially positive in both of these cases, but the partial positive charge is a little bigger on an aldehyde. So those two factors make aldehydes more reactive. It's just easier for a nucleophile to come in here and attack because there's not two R groups. It's more accessible sterically, but also that carbonyl has a more substantial partial positive charge, so it's more attractive for a nucleophile, which is either negative or partially negative. So these are more reactive generally. These are a little bit less reactive, but they do mostly the same types of things. And really, it's that partial positive, partial negative that defines the reactivity of aldehydes and ketones. It's because of the polarity of that bond that they do the things they do, and that's what we're going to talk about when we start looking at chemistry of these things that goes beyond just strong nucleophile attacking here and strong nucleophile like hydride or organometallic reagent attacking. They do more than that, so we're going to see that in this chapter. But first, let's talk about how to name them briefly. Naming aldehydes and ketones is not bad. It's pretty straightforward. There's just a few rules that you need to know to extend your knowledge of alkane naming to fit aldehydes and ketones. So we'll start with naming aldehydes because they're a little easier. You want to find longest carbon chain that contains the C double bond O carbon, because that's really the location of the functional group. That's the most important part of the molecule, so we're always going to look for that carbon to be represented in the longest carbon chain, and it's going to mark the 1 position as well. So I'll say these two things about it. C double bond O carbon defines the number 1 position. So you don't need to tell people where the carbonyl is located because everybody knows it's going to be on the end of the chain and it's going to be the 1 position. So like, for example, what if we had this molecule? What you do is count the longest carbon chain or identify the longest carbon chain. 1, 2, 3, 4, and then you number it 1, 2, 3, 4, and then we're going to use a little change at the end to specify that it's not an alkane, but it's a aldehyde functional group. So we're going to name as the alkane but drop the E ending and add al for aldehyde. So if this were an alkane, it'd be butane. So butane is the name of the 4-carbon alkane, but we're going to get rid of that E ending, and this is going to be butanal. Butanal. So the only thing we did is we just changed that little ending, and that signals to people, hey, this is a 4-carbon chain that has a aldehyde. And you know it's at the 1 position because it's always at the end of the chain with an aldehyde, but when we define it as the number 1 spot. So if you've got a substituted aldehyde, you can name the substituents and put numbers on them going by the numbering of the chain. Let's go through an example like that just so it's really obvious how to do it. And I'll throw a little bit of a curveball at you. I don't think this is going to be too hard, but here is a molecule that you might have to name. It is an aldehyde because the carbonyl has an H on it. So you got to find the longest carbon chain. And if you weren't careful, you might say, oh, it's 1, 2, 3, 4, 5, 6 carbons long. However, that longest carbon chain leaves out the carbonyl carbon, so you can't use it. It doesn't work. So you have to, might as well start your numbering and your chain finding at the carbonyl because you're going to have it. So just look for the longest carbon chain that starts there. And so if you do that, then you can wrap around like this and say, okay, there's my longest carbon chain. That's position number 1. There's 2, 3, 4, 5. So this is it'd be pentane if it were an alkane, so it's pentanal. And this has a ethyl group at the 2 position. So it goes 2-ethyl pent and now. And that's all you got to do to specify that one. There is a stereogenic center there, and if you saw dashes and wedges, you'd need to label that as RNS, but I'm not going to emphasize that on this exam because you know how to do that, you can figure that out, but really it's mostly about naming aldehydes as a new kind of functional group that you can attach a name to. Once in a while, you'll see an aldehyde attached to a ring. So if aldehyde is attached to an alkane ring, you're going to do something that's just a little different. Name it as the cycloalkane and add the suffix carbaldehyde. For example, suppose you had a 6-membered ring like this, and then off of it was a aldehyde group. So the way to make this simple as far as naming goes, the rules say just name it as a cycloalkane, so that would be cyclohexane. So the name of this thing would be cyclohexane, and then go right into carbaldehyde. And no space between the cyclohexane and carbaldehyde, just run it together as one big string of text. Also want to remind you that if you're dealing with a benzene ring that has an aldehyde on it, remember that has a special name. We learned about that a couple chapters back, several chapters ago actually. Just put it up here to refresh your memory. Just reminding you where you have a benzene ring that's attached to an aldehyde, that has its own special root name. This is called benzaldehyde. So that's, if you've got a benzene ring with an aldehyde attached, you call it that. Okay, questions about aldehyde naming? There's not much more to it than that. It's pretty straightforward. Ketone naming is a little bit different, a little bit more complicated because you have to specify the position of the carbonyl group in a chain because it's not at the end of the chain, it's somewhere in the middle of an alkane chain. So I'm going to talk about this, naming ketones. It's analogous to naming aldehydes, but you have to do one more step to tell people where the carbonyl is located in a multi-carbon chain. So find longest carbon chain. Find longest carbon chain that contains C double bond O carbon, and then number from the end that gives the carbonyl C double bond O the lowest number. So if you're looking at a ketone that looks like this, for example, you would find the longest carbon chain that contains the C double bond O, which is really all the carbons in the molecule, so this one is not difficult. But then you number it from the end that is closest to the carbonyl. So you don't want to start here because then you wouldn't get to the carbonyl until 3. But if you start here, call that a 1, that a 2, that a 3, and that a 4, that's the way to number it. So then you want to name as an alkane. Replace E ending with own. I know it looks like 1 when you see it out of context like that, but O-N-E for ketone. And put the number in front of own. So that number where it designates where the ketone carbonyl is located, just put it in front of own. So like to summarize this, the molecule, if it were an alkane, would be butane. But we're going to get rid of the E and we're going to replace it with own, and we're going to stick in this number locator, butane 2 own. So that is the way to name them. That is described in the textbook, and most of the questions in the homework follow that pattern. That's the newest version of the IUPAC rules, the International Union for Pure and Applied Chemistry, the standard setting body that decides what constitutes acceptable nomenclature. This is the preferred IUPAC name. There is an older version of the naming that you may see leak through in various places, either in the ALEX homework or when you're reading through other kinds of like textbooks and things. It just puts the 2 out in front of the parent name. You might also see it as 2-butanone. You won't need to know this version of the naming for the exam. I won't ask you questions like this, but I know there's at least a couple in the homework that still use the older nomenclature, so it's just a matter of like where is the preferred place to put the 2 or the number locator. Closest to the functional group is the logical place to put it. It makes it a little harder to say. Butane 2-one doesn't kind of like roll off the tongue as easily as 2-butanone, which is why I think the older version is still in use, but either one is okay. If you named it like this on an exam, I'd still give you credit for it. If you have to supply a name on an exam, any acceptable IUPAC name would be fine. But if you're like trying to draw a structure, if I say draw a structure like this, then you would see this version of the nomenclature, where the number locator is right next to the functional group, the own. So that's acyclic ketones. Cyclic ketones are a little simpler because they don't have an end to the chain. They they have a ring, and there's the rules get simpler then, because you can just say that the carbonyl group defines the number 1 position on a cyclic ketone, and that's the way that it works. So for cyclic ketones, name as the cycloalkane. Drop the E ending and add own. So pretty much just like the acyclic ketones. But here's the big difference, is that carbonyl carbon defines the 1 position. So you don't need to name it. So if you saw a cyclic ketone like this, for example, you would immediately give the carbonyl group a 1, because you're required to. It's actually nice. You don't have to think about it. You just put it there. Then what you have to do, all you need to do is decide, go around the ring to give low possible numbers to these groups. And so you want to go clockwise in this example, because then the substituents get 2s instead of 5s. So this would be the way to number this ring. It's very similar to how we number a lot of different rings. You just kind of want to, you have 2 options. You can either number clockwise or counterclockwise. Go the way that gives you the lowest number to the substituent, or substituents in this case. So this is a cyclo, the parent name, this would be a cyclopentane. So you get rid of the E, it becomes cyclopentanone. That'd be the parent name. And then you just have to specify that there are methyl groups in the 2 positions. So the full proper name for this would be 2-2-dimethyl cyclopentanone. 2,2-dimethyl cyclopentanone. And that is your name for that molecule. And notice how you had to specify the 2 twice. There were 2 methyl groups. You have to locate each one of them, even if they're on the same carbon. Just like we did with alkane naming. That was the same deal. Yes, question?
Maybe I'm getting a little ahead here, but what if the ketone is stemming off of a ring?
Good question. So what if the ketone were a substituent? Let's take a look at that. All right, then you'd probably, it depends on the ketone, it depends how big the carbon group is, but I'll give you the one scenario that you might see, which is one where the linear chain is larger than the ring. So here's an example of that. So if you saw this, for example, this crazy thing. Yeah, it's got a ring and it has a ketone, so that's kind of a way. But if you look at it, the biggest part of this is the chain, and really the most important thing though is the carbonyl is associated with the chain and not the ring. So you would name it as a ketone in this chain. So this would have one, and we got to give this the lowest possible number. If we started here, it'd be 1, 2, 3, 4. If we started here, it'd be 1, 2, 3. So we have to start from this side, give it a 1 here, a 2 there, a 3, a 4, a 5, and a 6. So it would be a hexanone that has a cyclopropyl group in the 1 position. So 1 cyclopropyl hexane 3-one be the way to name that thing. And I could dream up examples where the ring is bigger, but still the most important part is the functional group. So you got to name, you got to put, the carbonyl has to be given top billing. Whatever you choose as the root name's got to have the carbonyl in it. So the size is less important. Ultimate size of the ring or the chain is less important than locating the carbonyl within the root name. So anyway, the plan is not to have overly complicated examples on the exam, and you'll look through the homework and you'll see they're not weird, crazy difficult. They might test your ability to figure out where to start counting, where's the most appropriate spot to start your numbering, but they're not, it's pretty basic level of nomenclature. So I expect these will be pretty simple once you get the rules down. Once you get the rules down, it should be like, you should get the right, hopefully you get the right answer every time, unless you make some simple mistake or something. Okay, that's all you need to know about naming. Do you have any questions about the naming of aldehydes and ketones? All right, then we get on to the interesting stuff, which is their reactivities. There's a lot of preparation of aldehydes and ketones that has been covered in the past. Lots of actually throughout the course, and there's some good chapters and sections in the Smith textbook that reviews how do you prepare aldehydes and ketones. So if you remember back to chapter 12, oxidation reduction, you could oxidize secondary alcohols to give ketones. You could oxidize primary alcohols using PCC to give aldehydes. There was oxidation of alkenes using ozone to give aldehydes and ketones. There's all sorts of different preps that we've looked at before. That is good to look at, but it's not going to be the focus of what we're doing now, because we're going to look at new stuff now. So preparation of aldehydes and ketones using existing methods is covered in the chapter, and it's good to look that over. But let's get into some new stuff. And what I want to do is get into the Wittig reaction, because that is one of the big reactions from this chapter that's a little different than what we've looked at in the past. We've seen hydrides, strong hydride sources adding to aldehydes and ketones. That's a nucleophile of an H- adding to a carbonyl. That reduces it. We've seen organometallic reagents, a carbon nucleophile attacking a carbonyl group and giving an alcohol. So we've seen those, but here's a new nucleophile that we're going to talk about. This is the Wittig reaction, and we did it in lab last week. So here we are going to see it in lecture. What is the Wittig reaction? How does it work? What's it good for? What is its mechanism? What are some strengths and weaknesses of it? Because everything's got strengths and weaknesses. If you think about these reactions as kind of like tools in a toolbox, just like, tools that you might pull out and use for some kind of job you've got, there's, some tools work better than others, and one tool isn't the best for everything. So these reactions are kind of like that, and that some of them work really well under certain circumstances. In other cases, they don't work well or work at all. So we're going to start talking about the Wittig reaction now. So the Wittig reaction is a really important one in organic chemistry. It's a powerful reaction because it allows you to stitch two pieces together and make a carbon-carbon bond. So that's what this is all about. It's good for making alkenes. So if you need to make a double bond in a molecule, Wittig reaction is a pretty good choice. It's one that's designed to do that, and it does its job pretty well. Let's talk about where it works, how it works. This was, by the way, subject of a Nobel Prize back in 1979. Goes back quite a ways. George Wittig was the chemist that shared the Nobel Prize. This reaction, there was another, I think the prize was split a couple of different ways in 1979, but it's considered really important, and it still holds up well today, but it has a few weaknesses we'll talk about. So what I'm going to do first is go through that example that we talked about in lab, or one that's very similar to it, and then you can sort of see how all the steps work out. So here's how it starts. It starts with a species that's called a phosphonium salt. So the phosphonium salt that we used in our reaction had a phenyl group here. This could be, these groups could be anything. There needs to be at least one H on a carbon that's attached to a phosphorus, and then the phosphorus has 3 phenyl groups. And maybe what I should do is, while we're getting used to this, I'm going to draw in all the phenyl groups so that you have an appreciation for where they are. So phenyl group is just benzene ring attached as a substituent. So this phosphorus has got 4 bonds to it. It has a formal positive charge. And then there's got to be a counterion to it, and it could be many different things. Chloride is one option. In lab last week, we used a chloride-based salt. Could be bromide or iodide, but there it is with a chloride salt. Now, these phosphonium salts have protons that are on this carbon. So that carbon right there, these protons are weakly acidic. Which means that you can pluck them off with a strong base. The other protons in this molecule are not weakly acidic. They're just not acidic at all. So they're gonna not get plucked off by a strong base, but these are potentially abstractable. And so you put in a strong enough base and you can pluck off one of those H's. And in our case, in our reaction, we used hydroxide. Hydroxide is one option. You could use other bases as well. Sometimes really strong bases like N- would get used, or an even stronger base like a organolithium reagent could work here. So if you saw phenylithium or magnesium or methyl magnesium bromide or something, think, okay, that's a species that is a nucleophile but also acts as a base, and plucks one of these off potentially. So what happens is the hydroxide grabs one of these protons, and in this case there are 2 and they're identical, and you get, as an intermediate, this species, which now I'm going to abbreviate the phenyl groups as pHs just to make it a little easier to draw. Except for this one. I'm going to draw this one out just to keep track of it. So that gives this species. So we've deprotonated the phosphonium salt and we have this thing. And now this is charge neutral because the molecule has a positive and a negative charge within it. And there's a resonance structure for this that works like this. A carbon-phosphorus double bond can form, and this is just another of 2 important resonance structures for this molecule. Both of these describe the same molecule, though. It's a phosphorus that has a lot of partial positive charge on it, and a carbon that has a lot of partial negative. And collectively, like I said, these are resonance structures. This is something called a phosphorus ylide. Spelled Y-L-I-D-E, pronounced ylide. And what that means is it's a molecule that's got a positive and a negative in it adjacent to each other like this. And that's the intermediate that you need to do the Wittig reaction. So sometimes you'll be given a reaction where they'll give you an ylide structure to work with, and they'll toss in the next reagent, which is an aldehyde or ketone. Sometimes they'll go back a step and give you a phosphonium salt. and ask you to go forward with that. Sometimes they'll even go a step backwards further and ask you, where do you get this salt from? And we'll talk about that in a little bit. Hint, though, it's an SN2 substitution reaction, so it's really not new chemistry. We'll point that out later, but for right now, we're looking at, okay, we have a phosphonium salt. We just plucked a proton off of it. We made this ylide species. Then what happens is it reacts with an aldehyde or ketone, and that's why it's in this chapter. Because this chapter is all about reactions of aldehydes and ketones. Okay, so I'm going to slide this over a little bit. There we go. And show you what happens next. There'll be an aldehyde or ketone that gets put in with this. And our aldehyde in lab last week was a pretty big one. It had... get this bracket down a little bit here. It had a ring system that was pretty complicated. It doesn't have to be a giant aldehyde like this, but this is what we did in lab. So I'm just going to give you this example because you've seen it before. And the reason I'm drawing it like this is the aldehyde has a polarized bond as well. It has a partial negative charge on the oxygen and a partial positive charge on the carbon of the carbonyl. That's one of the things that defines how it works. And it likes to arrange itself like this because then the oxygen of the carbonyl that's partially negative can associate with the partially positive phosphorus. And then over on this side, the partially positive carbon of the carbonyl can associate with the partially negative carbon of the ylide structure. And so it lines itself up like that where the complementary charges are associated. And then electrons flow. And the way that they work is that they flow from the phosphorus carbon bond. Carbon takes those electrons and moves to make a new bond to that carbonyl carbon. And then the electrons in the carbon-oxygen bond, they go to form a new bond to phosphorus. And what you get out of this is a new species. It's an intermediate where we've made a ring. So we have a oxygen-phosphorus bond, and there's a carbon here, and there's a carbon here, and a bond there. The phosphorus still has its 3 phenyl groups. The carbon that was part of the ylide structure still has its groups. There's still a phenyl group attached there, and a hydrogen. And then what came with the carbonyl was an H and this big anthracene ring system. So everything still kind of comes with. So it's just a matter of like keeping track of what bonds are forming and what bonds are breaking. But this species is an intermediate that's called an oxyphosphatane. And it's an intermediate that actually is a 4-membered ring. All right. This stays around for just a little while, and eventually it breaks down, though, and becomes 2 separate molecules. So what's going to happen is the molecule is going to break in half right here. And the molecules on the left are going to go one way, and the molecule, or I should say the molecules, the atoms on one side are going to go one way, and the atoms on the right side are going to go another way. So these 2 bonds are going to break. So we're going to shift 2 pairs of electrons around. It doesn't matter which direction you show these going, but I'll just start at this bond, break it, and push the electrons over here. I think I'll use the white chalk because that's like by convention what I've been using for this mechanism, like this. So this bond breaking is going to make 2 separate molecules. And it's going to give us a piece where the phosphorus has a full double bond to oxygen. This molecule is called triphenylphosphine oxide. Phosphine oxide. And the feature of it is that it has a very strong bond here. So although this is a product that is a waste product, nobody does the Wittig reaction to get this species, its formation is important in getting the whole reaction to go. Because along with that, you get the alkene that you're interested in, and in our case, in our experiment, we got this molecule, which was 9-styryl anthracene. I think it's a styryl anthracene. Anyway, the name isn't that important. What really matters is that it's an alkene, and it happens to have these groups on it. And the molecule itself came from the two different materials. So if you were to analyze this and ask yourself, where do the carbons come from here in these cases? If you drew a line right down the carbon-carbon double bond, on one side you get the atoms that came from the ylide structure. And then on the other side, you get the atoms that came from the carbonyl group. In our case, it was an aldehyde. So I'll say this part came from carbonyl compound. This part came from the ylide. So that's how it shakes out. Let's go through a few examples to see if we can predict products, and then we'll talk about where do phosphonium salts come from and how can you work through how to make one. All right, let's take a look at a couple of different kinds of questions, Wittig type questions. All right, so predict the products. What would you get if you put this structure, and I'll just put a bromide up here for variety, and you added it with, and you did first treatment with the strong base. Hydroxide is one option, but what if you treated it with, like, say, for example, this organometallic reagent, butyllithium, and then you put it in with, oh, maybe like a ketone like this. What would you get? Well, the first thing you would get is you deprotonate this with the organometallic reagent. I'm going to actually show that step because a lot of people miss this when they see it on a problem set or on an exam. They're not quite sure what butyllithium does, even though they know it's a strong base, and they know they're more familiar with it attacking carbonyls than they are with it deprotonating things. But organolithiums have strong partial negative charge here, and these H's are subject to deprotonation. So this is just using the butyllithium as a really strong base. And then there's a resonance structure where the phosphorus would look like that, basically. So that's the first step, is you make an ylide using the strong base. Could be lithium, organolithium compound, could be hydroxide or some other strong base. But once you have that, then it reacts with the aldehyde or ketone. And the aldehyde or ketone, remember, the way to position it is put, and I'm going to just fold it up like that to make it a little bit more compact. But line it up like this, where you get the partial negative and partial positive of the carbonyl lining up with the partial positive and partial negative of the ylide species. And then you draw the four-membered ring intermediate, which would look like this. You get the phosphorus attached to the oxygen. There are 3 phenyl groups here. There's 2 ethyl groups attached here. Down here, there's a methyl group. And then the molecule breaks down the middle. And you get triphenylphosphine oxide. You always get triphenylphosphine oxide in the Wittig reaction if you use triphenylphosphine-based phosphonium salts. And then the species you're really interested in here is this one. So that's one example of a Wittig reaction. If you have a Wittig reaction that can give 2 possible stereoisomers, you will usually get both. I'm going to show you an example of that next, just so you get used to it. If you were to see, for example, this Wittig reaction, and there may be questions in the homework, and there might be questions on the old exams like this, where you are given a set of reactants that could produce an alkene product that has stereoisomer possibility. So like, for example, here's an example of that. So I'm going to give you a phosphonium salt here. Not a salt. I'm going to actually give you the ylide structure. So, because sometimes you're given this, the instructions will be like, you know, we're going to skip the formation of the ylide. We're just going to give it to you, and we're going to give you some kind of a carbonyl group to work with. In this case, I'm going to give you benzaldehyde. You know, what comes out of this? Well, you're going to line these up so that the phosphorus and the oxygen are together, and the 2 carbons are together like that. And then you form an intermediate. It breaks down, and you get triphenylphosphine oxide as the one predictable product. It's always the same, but then you get out an alkene that has as one substituent an ethyl group, and as the other substituent a phenyl group. And so there's 2 ways to do that. There's the cis molecule, and then there's a trans version of it too. And with the Wittig reaction, you might predict trans is more stable, so maybe it's the major product, but it doesn't always work out that way, or it's not always different enough that you just get one. And so there's 2 possible stereoisomers here. You get the cis and the trans. And what I'm doing is, to get cis and trans, is I'm just like imagining like bisecting the carbon-carbon double bond here. And in this case, the ethyl group and the phenyl group are on the same side. And in this case, they're on opposite sides. So that's why one is cis and one is trans, and they both are possible. So Wittig reaction can give mixtures of stereoisomers. The truth is it's kind of complicated, and we're not kind of try to expect you to predict what's going to be major and minor, because it's kind of a complicated problem. But just know that both are possible. So so you won't like just focus on one, and know that there are stereoisomers can happen sometimes. Like in this case, that alkene could exist in two possible non-superimposable like orientations. Okay, so really quickly then, where do phosphonium salts come from? So this will be pretty easy to cover in 3 minutes because you've seen it before. It's an SN2 substitution reaction. So if you need to make a phosphonium salt, what you do is you start with triphenylphosphine, which is this molecule. It's a phosphorus that has 3 phenyl groups on it and a lone pair on phosphorus. And then you add whatever alkyl halide it is that you need to make your phosphonium salt. So like, for example, suppose you wanted to make, put an ethyl group on your phosphorus. Well, you just start here with this ethyl bromide, and what happens is this is an SN2 substitution reaction where the phosphorus comes in, attacks backside, bromide gets bumped out, and then you get a phosphonium salt where you've got that. So this is just an SN2 substitution reaction like you're used to seeing from last semester. Hopefully you remember SN2. It's nucleophile, attacks alkyl halide. Things we're going to talk about next time. This steric hindrance matters in this step. So if you're trying to make a phosphonium salt, remember SN2 has certain limitations and steric hindrance is one of them. So this is one that's going to work well because this is a primary alkyl halide. But secondaries aren't so good. So we'll talk about, and tertiaries don't work at all. So we'll talk about that next time and the limitations that you have in making a phosphonium salt. But this is a phosphonium salt. And you can use it to make an ylide, which you can then use to do a Wittig reaction. So we'll talk a little bit more about Wittig next time, and then we're going to move on to acetals, which is another class of aldehyde ketone kind of derivative that's really important. So I will see you in lab tomorrow if you're one of my lab students this semester. So we'll be doing brand new chemistry aldol, which we're going to cover in lecture after Thanksgiving.